Okay, part C, we have x minus 3y plus z equals 4, x plus 5y minus z equals 2, negative 2x plus 2y minus z equals negative 7. Okay. You guys tell me, which variable is easiest to eliminate here? Z. So I designed these problems so that you wouldn't pick x every time, right? And to see that you don't want to get stuck in that rut of picking the same variable to eliminate every time, because you'd make your life harder if you did that. All right, so just what do you want to do with, how do you want to do it? You tell me. E1 and E2 sounds good to me. E1 plus E2. Okay, add those up. What do we get? So yeah, 2x plus, okay, we have a minus 3y plus 5y plus 2y equals, okay, the z's are gone, equals 6 again. That kind of looks like what we had last time, except I think it was different variables. Divide through by 2, what do you get? X plus y equals 3 again. Okay, cool. Okay, so, and I didn't label them, but once again, you know that the top equation's E1, the middle one's E2, and the third one's E3. Okay, so that's step 1, isn't it? And then step 2, you want to use the equation you haven't used yet, a different set of 2 equations. One of them has to be the same, one of them has to be different. If you have 3 equations, 3 unknowns, that is. And then eliminate the same unknowns. So how do you want to do that? E1 and E3 makes sense, yeah. So E1 and E3, we're going to add those together. E1 plus E3. All right, so E1 and E3, so add them up. What do we get? X plus negative 2x, what does that make? X plus negative 2x, negative x. Negative 3y plus 2y. Z plus negative z. We're looking at the first and third equation, right? Gone. And then 4 plus a negative 7. Negative 3. Okay, so we've got our 2 equations and 2 unknowns. Remember what step 3 says. It says solve that resulting system. X plus y equals 3 and negative x minus y equals negative 3. The natural thing to try and use is which method, elimination or substitution? Elimination. What happens when you add both equations together? 0 equals 0. Now, is that true or false? Last time I looked, that was true. So what you have here, whenever you get a true statement, whether it's 2 equations, 2 unknowns, 3 equations, 3 unknowns, a million equations, a million unknowns, what happens is, if you get a true statement like this, it's a dependent system. Which means there's an infinite number of solutions. Now, I'm not going to make you try and characterize it like we did in the last section. So you're not going to have to use set notation or ordered pair notation. You'll do that in your next class. You don't have to worry about it here. Just be able to mark it dependent when you get a true statement. What do you think is going to be true when it's a false statement? No solution, right? So what's the situation then, do you think, graphically? So let's graph the 3 original equations. The first equation graphs to be that plane in blue. Second equation in green. Third equation, I don't know, it's kind of a gold color, I guess, depending on how the light hits it. And so the 3 planes intersect, but not in a point. They intersect in a line. In fact, I actually graphed the line here for you. They intersect in that line. And that line contains an infinite number of ordered triples, which is why it's a dependent system. And then when you get no solution, which I haven't shown you an example of yet, you'll see one in the homework, at least 2 of the planes just don't intersect. They're parallel to each other. In the next example, let's solve the system of 3 linear equations, 3 unknowns. 1/4 x plus 1/4 y plus 3z equals 1/2 is your first equation. 0.2x plus 0.2y plus 2.4z equals 1 is the second, and 3x plus 4y minus 2z equals 7 is your third equation. Okay, don't let fractions or decimals freak you out. In this top equation, we can clear the denominators, clear the fractions, by multiplying both sides by the LCD. And the LCD, if you look at all the denominators, we have 4, 4, and 2. The LCD between 4, 4, and 2 is 4. So just multiply each and every term on both sides by 4. And you will clear the fractions if you do that. So we do that. I'm going to write the result over here. 4 times 1/4 x is just 1x, or x. Plus 4 times 1/4 y, so just plus y. Plus 4 times 3. 4 times 3z is 12z. And then 4 times 1/2 is going to be just 2. In this second equation, if you don't like dealing with decimals, well, you don't have to. You could actually multiply through by 5, but if you don't see that, the obvious thing to do to get the decimal to move over to the right is to multiply rather by 10 if you want to move it once to the right. But if you do that, you get like 2x plus 2y plus 24z equals 10, which is divisible by 2. So if you want to do it all in one shot, you could multiply through by just 5. And then that'll give you 5 times 0.2 is 1x. So 1x, or just x, plus 1y, 5 times 0.2y. And then 5 times 24 is 120, so, move the decimal point, that's also 12. So 12z, 5 times 2.4z is 12z, equals 5 times 1, which is 5. Remember to multiply both sides by 5. And then the third equation we don't have to do anything to right now. I'll just recopy it. 3x plus 4y minus 2z equals 7. So we're going to solve this system of equations. And it'll have the same solutions as the original system. And you may notice that on the left-hand side in the first two equations, you have exactly the same thing. Let me label these guys. As usual, E1, E2, E3. And so what I'm going to do, I'm going to think of it as just eliminating the x's, but then we're going to end up eliminating all of the variables as well. If I eliminate the x's, okay, here's one way I can represent it. I can multiply E2 by a -1, or just write it as negative E2, and then add it to E1. So symbolically, that's what I'm doing. And I'm going to multiply this guy, that's E2, by then -1, or just negative. Just a negative, that is. And then if I do that, that just makes all the signs opposite. So negative x minus y minus 12z equals -5. And then I'm going to add that to E1, which is x plus y plus 12z equals 2. And if I do that addition, everything zeroes out here on the left side, and I get 0. But on the right side, I get -3. Not true. That's a false statement. And when you get a false statement, you know there's no solution. So that's it. We just write down no solution. It's an inconsistent system, which simply means it turns out in this case at least, two of the planes are parallel. So you're not going to get a common intersection point or points between all three planes if you graph them.